Welcome back. So, in today's video lecture, we will look at the van der Waals forces in detail. Okay. As you know, there are three types of forces within van der Waals forces. We will look at them in detail. Okay. And apart from that, we will also look at how to calculate the pairwise interaction between the molecules and or between the macroscopic bodies which are made up of its own constituent molecules, right? Sometime you may have to do the pairwise interaction between flat surface as well as the curved surface or between two flat surfaces, like so. By knowing the the I mean the by knowing the calculation part of the pairwise interaction between these two bodies, one can calculate for numerous cases, right? So these are something we will look at in detail in this video. Let's begin. So, as you know, van der Waals forces meaning it has got three different forces which are nothing but the induced dipole, okay, which is nothing but London or dispersion force, induced dipole, permanent dipole, which is also called as d by, and permanent dipole, which is nothing but Keesum, right? So remember, when we dealt with the Lennard-Jones potential in previous lecture, we we discussed that the attractive term, which is inverse power law, dependent on the separation distance, is nothing but it has got a prefactor that is called B, right? That B comes from the beta. So the beta is nothing but the the constant value, the combination of all the constant values coming from the London and d by and Keesum forces, right? So that is what I mean. That we have also that we have described in the previous lecture itself. So so that is very important to note. So now we will uh, see what are the implications of these forces, right? Sometime you will only have to focus on one or two forces, not all three. For example, whether you deal with the polar molecule or non-polar molecule, okay, charged system or uncharged system, the London or dispersion force is always existing. This comes from the fluctuation in the electron density within the atom or molecules. So you can expect this force always, right? So sometime you might deal with the polar molecule together non-polar molecule. So there can be an interaction between polar and non-polar. In such case, you would expect an interaction between interaction in the form of induced dipole and permanent dipole, which is coming under the d by force category. The other one is the permanent and permanent dipole, which comes from the molecule which has got dipoles permanently, right? For example, acetone, acetaldehyde, HCl, and all those things. Okay. So as we can read from here, the Keesum force is because of the electronegativity, right? Due to electronegativity. Okay. Um, so it is basically because of the permanent dipoles, right, between the molecules, and that is due to the electronegativity. And you can also understand that you can also read that the induced dipole and permanent dipole, which is d by force of attraction, is basically between polar and non-polar molecules, right? Okay, so in any case, van der Waals forces are always attractive. Okay, so we often use the sign convention negative to represent attractive force, positive to represent repulsive force. Okay, So it is always long ranged force, relatively long ranged force compared to atomic or molecular level forces. And more importantly, the van der Waals forces of attraction is active within the separation distance, of between zero point 0.2 nanometer to 1 nanometer. Okay, from 0.2 nanometer to 1 nanometer. So which means that if, let's say, you have got the molecules, right? So if molecules are kept apart within a distance of 10 nanometer, then we can expect all these three forces, come into picture. Okay, right. So next we will look at the inverse power law, molecular interactions and inverse power law. Okay, if you want to calculate the interaction between two colloidal particles, spherical particle or non-spherical particle, or between two macroscopic objects like blocks, between two blocks, or between surfaces, one flat surface and the curved surface, all that, you can actually use this method of the calculating the pairwise interactions, right, between the molecules or particles, right. Okay, so as you know, there are three different types of forces under van der Waals forces. Okay, you can see that these three equations, right, d by Keesum and London, uh, all these equations are inverse power law dependence. So show all these three equations show inverse power law dependency, right, on separation distance, that is x. Remember, we saw in the Lennard-Jones potential, that is a b by x power 6, right. Okay, you can see the similar relation exists over here. Here b is nothing but beta, which means that if you include all these constants, right, as within the bracket of beta, then you will be getting this beta x power 6, right. So yeah, so this comes from the you can now connect this with the potential that we have already described, right. Right. So these three forces equations, you can the origin of this equation, if you want to understand the origin of these equations more in details, maybe you can refer to these two books which are given at the bottom below. Okay, right. Now let's see, because these are the power law, inverse power law equation, it can be applied, whenever we calculate the pairwise interactions of molecules or the between the particles, right. Um, right. So first, let us understand the permanent dipole and induced dipole. So d by equation. So basically, the London. Let's start with the London. Basically, the London force, which is always existing, right? Which is always existing, no matter whether whether you deal with charged system or uncharged system. Okay, it is because of the fluctuation in the electron density, right. So that's how you get the London force always. So let's say you deal with an atom which is neutral atom or argon. Let's say, for an example, we can say argon, we deal with argon, and there is another neighboring atom which is also an argon. When there is an interaction between the two, how they will interact, right. So as you know, that every compound has got its own electrons density within it. Okay, it depends on the atomic mass or molar mass of the compound that we deal with. For example, if you take an example of helium, which has got only 2 electron, whereas argon has got about 18 electrons, right. So the probability of argon atom, okay, breaking the symmetry of distribution is highly likely compared to the helium, because it has got only 2 electron, right. So you can expect more of these the London dispersion force in the case of argon will be more likely than the helium, right. So you can see that how this is actually this dipole among these molecules are induced, right. Okay, so you can see that there will be an atom. If you take an example of organ, there will be a nucleus, and then around it there will be electron density, right? Electron cloud, right? So if electron cloud shifts one side, right, because they will be randomly moving around, at some point of time the electron cloud will be more on one side and less on the other side. So you will have more electron cloud on one side and less on the other side. In such case, naturally this molecule at one end it will gain net negative charge, right? There will be it will gain net negative charge on one hand, and because of which it will gain net positive charge on the other end. Okay, and a similar way, if other neighboring atom also experience the similar change, shift in the electron cloud, then you can expect that they will interact via the, so there can be net negative and net positive, right? So sorry, I think so. I want more electron cloud this side, less electron cloud. Yeah, so let less electron cloud. So more electron cloud this side, less electron cloud. So you will have again net negative charge and net positive charge. So there will be electrostatic attraction between these two end, right, where you got net positive and net negative. Although it is because of the electrostatic attraction, eventually the main reason for this attraction is because of the induced dipole. That is because of the changes in the electron or fluctuation in the electron density. Okay, you can give an example. Let's say argon, right, methane, which is a non-polar molecule, they will undergo this kind of an interaction. London dispersion force is very common among these molecule or an atom, right? So we talk about the induced dipole. You can also look at now what is known as permanent dipole. So one can give an example. Let's say we can take an example of acetaldehyde, right? If you take an example of acetaldehyde, let's say you got acetaldehyde has got C double bond O within it. Okay, because the oxygen has got more electronegativity, it will hog more electron towards this, right, towards it. So naturally this will gain net positive negative charge, right, because oxygen atom is more electronegative and it can hog more electron towards it, right? And uh, and because of which, if the center of mass is somewhere here, there will be net positive charge somewhere on the opposite end. Okay, so in this way, this molecule uh, will carry permanent dipole within it. Now, the neighboring atom will also carry similar dipoles. So, when positive and negative dipole interact with each other, there will be an attraction. Yes. So now, in this section, we will look at the how to calculate the pairwise interaction between two semi-infinite blocks. Okay. So what is given here is the WR, which is nothing but the interaction, right? Energy per molecule. This is basically energy per molecule. So idea is if you know the pairwise interaction, by summing up the interactions of all the molecules present between the black two semi-infinite blocks, then you will be able to obtain equation for this case, right? That is the exercise now we have got. So now what we will do is remember you have the, so the first approach will be, so you have two blocks, right? Okay, so first we will look at the one molecule from here, and then we will consider in a very region of space a small control volume, right? Small control volume, right, which is a ring shaped control volume. Okay, And if we consider this very small tiny control volume, so in this region of space, in this ring shaped control volume, you will have several molecules, right? The projection view of that will give you, okay, so you will be able to perform the pairwise interaction between this molecule, which is one, to several molecules present within this ring shaped, right? Okay, so once we know that, then by performing integration, right, from initial from lower limit to upper limit, right, you will be able to complete the pairwise interaction of entire block. Okay, so that is the idea, and that is what also shown in this schematic. Okay, so we will do that. So first of all, we know that when we want to do the sum total of all the molecular interaction, we know this is the function, this is energy per molecule, right? So when you multiply this with the rho Na by Ma, so this is basically uh, you know number of molecules per unit volume, okay, multiply by the dV, right? And integral. So if you perform this, basically you will be able to get cover all the molecules present within this region of space, that is called dV, right? And then you will be able to calculate the pairwise interaction for all the molecules. So in this way you will get total energy. Okay, so that is the exercise we have to do. So for here, let's consider this case which is shown in the schematic already. Okay, in this case, how we can write, right? So you can write this as, let's say we have WR, okay, into rho here is the density, and Na is the Avogadro number, and Ma is the molecular weight. Okay, A represent the molecules of particular species, right? And multiply by here the dV will be, for us in this schematic, we are considering between one molecule from block another block to this ring shaped. Why this is ring shaped? Because we consider that the molecule which we take is spherical in shapes, right? So the projection view of that will be a ring shaped. That's why we consider this ring shaped control volume, right? So in this case, the dV is going to be, for me, it will be simply 2 pi y dy and d zeta. Okay, this is just zeta is just a simple you can name any letter, right? Okay, so since we have dy and d zeta, we will have to do, there will be two integral going from 0 to infinity, 0 to infinity in this case. So if you perform this calculation, what you will get is the pairwise interaction between, right, between this molecule and the control element present in the block 1, right? So that is very clear. Once we are able to do this, then by performing integration from the lower limit to upper limit, okay, you will be able to consider or cover up all the molecules present within the block 1. That is the first exercise. So we are breaking down in this step into two. First step will be to take care of the molecule from block 2 to the molecules, all the molecules present in the block 1. That is exactly what we are doing here. Okay, right. So we have minus over here. Okay, that will be minus because it's attraction. Okay, so now what we can do is, so what is WR? So that we have to incorporate. Okay, so WR is nothing but beta by x power 6, and which is also okay, rho Na by m. This will come as it is. Then you have 2 pi y dy d zeta. Okay, so now all these things are constant. We'll keep the constant term outside. Okay, so which means that you can keep this constant term outside. Then you will have 2 pi. So minus 2 pi. Okay, rho Na by Ma and beta. So these things will be outside. Then you have 0 to infinity 0 to infinity, then you will be having x power minus 6, right? X power minus 6 y dy and d zeta. So, if we can perform this, then we will be getting some idea, right, what is the pairwise interaction, right, in this within this control volume. So, we know from the Pythagoras theorem, this x can be x square is nothing but z plus zeta. So, you can look at this geometry, okay, and you can understand why we call it as z plus zeta square plus y square, right. So, from Pythagoras theorem, we can write this x square as z plus zeta square plus y square. So, why we have done this way? Because it is easy for us to obtain the equation in terms of z, that is z direction, that is z. Why? Because it is easy for us to know what is the separation distance. So, your equation finally that you will be getting will be in terms of separation distance d, right, that you will see exactly how it is coming. So, now we have z plus zeta square plus y square. So, we will substitute this here. So, in that case you will be having this equation is simply nothing but minus 2 pi rho n a by m a, okay, beta. So, one integral we can perform now, which is here it will be z plus zeta square plus y square, and you will have minus 3 and y dy, right, okay, and then you have dz, okay, and this one is integral from 0 to infinity, okay. So, by using the substitution method, you can actually evaluate this integral, that is nothing but, let us say if I assume z plus zeta as m, okay, and this will be m square plus y square as u, okay, then 2y dy is nothing but du, and y dy is nothing but du by 2. Now, integral will be going from instead of 0 to infinity, it will be going from m square to infinity, right. Yes, m square to infinity, right. So, this will be m square to infinity, correct. So, if you perform this equation, I mean in this way, after substituting this as u z plus zeta square plus y square as u, you will be able to get the required you will be able to perform required integration and get the final answer you will be getting is, you can also verify, that will be 1 by 4 z plus zeta to the power 4. So, this is exactly what you will get, okay, after substituting this after performing this integration using substitution method, okay. So, what will be left out is there is another integration we have, that is d zeta, right. So, this entire thing will be coming as it is, okay, all right. So, now if you perform this again, let us say we have minus yeah, minus 2 pi rho n a by m a beta, okay, and yeah, divided by 4, that's 4 here, right, yeah, and 1 by, right, z plus zeta to the power 4 d zeta. So, if you have to evaluate this integral again, so again you can substitute this z plus zeta as u, right, then d zeta will be simply du. The limit will be going from, instead of 0 to infinity, it will be going from z to infinity. So, that is exactly you have to substitute here. So, if you substitute again, you will get the equation, the final equation will be minus 2 pi rho n a by m a. It will be beta, there will be, yeah, so beta by 12, right, and z cube. So, this is exactly what you will have. So, you can cancel this. So, you will have minus rho n a by m a, okay, into beta pi divided by 6 z cube. So, this is exactly what the the integration. After performing the integration, you will have. Now it is not done. So what we have to do further is, so you need to again, there is another one, right? So we have now taken care of one molecule, and then we summed the pairwise interaction, we performed pairwise interaction, within the molecule present in the block 1, right? Now we need to do the same exercise for the block 2, right? So now how do we do? Remember, imagine we are going to cut this small slice, right, from this, okay, and in that small slice you have molecules present, right? Okay, the advantage here is the molecules, all these molecules are at the same distance, which is same separation distance d. In that case, what you can do, since we have already calculated for one molecule in this case with all the molecules present in block 1, if by multiplying the number of molecules present within this slice, the small slice of block 2, you will be able to calculate the pairwise interaction of all the molecules between block 1 to the small slice, the thin slice of this block 2. In that way, you will be able to get the pairwise interaction up to this point, right? Right. So that is exactly we will do. So that is nothing but then you will have to multiply that with rho Na by Ma. So you will have simply then rho Na by Ma square. Okay. Then this is minus. So beta pi divided by 6 Z cube. So this is exactly what we have. Now by performing integration from this point to up to whatever extension, I mean to whatever extent that is required. For example, it can be from d. So this is the d is the separation distance. So from d separation distance to, you can go up to any astronomical distance, that is infinity. If you perform integral, okay, in this case, let's say if I perform integral between d to infinity 1 by z cube into dz. In this way, I will be able to obtain the pairwise interaction of all the molecules present in the block 2 as well as block 1. So that is what exactly we wanted to do, and that is exactly what we are going to do. Okay. So in this way, what you will be obtaining is rho Na by Ma whole square, okay, beta pi by 6, right? This will be simply what you will get is 1 by d square. So by performing this, you will be getting as 1 by z square. So it will be 2z square, right? So you will have, this will be 12. So finally you will get 12. Okay. So now if I assume that there is something called Hamaker constant. Okay. So if I assume Hamaker constant as capital A, okay, and so all these things I can put into this bracket. So I can call this Hamaker constant as rho Na, okay, pi divided by Ma whole square. So since I have taken one additional pi and put it inside the bracket, so I just have to also add one more pi in the denominator, right? So this is nothing but Hamaker constant. Okay. So in this way, I can rewrite this equation, the old equation as, so then old equation as this, let's say pi, if I say that is the total energy, that is nothing but minus A, okay, by 12 d square. Okay. So A is nothing but Hamaker constant. Okay, and that is nothing but rho Na pi by Ma whole square into beta. So beta is also included in this A. So this is how you can calculate the pairwise interaction of any two macroscopic bodies which are made up of its own constituent molecules, right? So I think it would have been very clear to you. We will stop here. We will continue from the next lecture. Thank you.